Hello, and welcome to the video accompaniment for Chapter 7, Section 1 of our text. In this video, we'll be talking about divisibility properties. Now, this whole chapter, Chapter 7, is about integers. And so one fundamental concept that we'll need to understand the integers is this idea of divisibility. So when one integer divides another integer. So after reading through the section and watching the video, you should understand and be able to apply the terms divides, multiple, factor, divisor. So be able to pick those out. As well, you should be able to prove some general results about divisibility. And so we'll look at some of those in this video, but there are a couple others in the book, a couple other examples that you can look through, and then in your homework, you'll prove some more properties about divisibility here. All right, let's get started. Now, while I always encourage you to read through the section before the video, I thought it might be useful here to just talk about some terminology related to this, really drive home the definition, the main definition that we encounter in this section, and that is the concept of dividing. What does it mean for one integer to divide another integer? So for integers a and b, and here we'll assume a is not equal to 0, we say that a divides b if b is equal to a times c for some integer c. So if we can find this integer c such that b equals a times c, we say a divides b, and we write a, I'll underline it here, we write a vertical line b to mean a divides b. So one thing I'll point out is that a divides b, one thing I've seen students do in the past is they think a divides b, this means like a divided by b. Well, a divided by b is an operation, right? So I could say something like 10, divided by 5. Well, I know that that's like a computation, that's equal to 2. But in this case, right, a divides b, a vertical line b, that's a statement. It's not some computation, it's a statement. And so if 10 divided by 5 is equal to 2, well, actually we can say something about divisibility here. We can say that 5 divides 10. And this doesn't equal anything. Again, I really want to drive that home. This doesn't equal anything. This means, this is a statement, this means 5 divides 10. And why is that true? Well, 5 divides 10 because, so if I wanted to say prove that, although that's not really something you would need to prove, but if I wanted to prove that 5 divides 10, well, I need to find some integer c such that 10 is equal to 5 times c. In that case, c would be 2. So I could say 5 divides 10 because 10 is equal to 5 times 2. So like in our definition here, 10 is our A, 5 is our B, and 2 would be our C, this thing that we have to find to prove that one number divides another one. So for example, well, I just kind of gave you an example up there. I'll just draw an arrow up there. That's what it means to divide, when one integer divides another integer. All right, so some other terms that go along with this. So if A divides B, so think back up here in this example like 5 and 10, then we say A is a factor or a divisor of B. So up in this example, we say 5 would be a factor of 10, or 5 is a divisor of 10. And B would be called a multiple of A. So 10 is a multiple of 5. And that sort of makes sense, right? Because 10 is 5 multiplied by 2. So it makes sense to say 10 is a multiple of 5. It's some multiple of 5. So let's take a look at a couple other examples that we can talk through here. So for example, let's say -7. So I'll write down the statement, -7 divides 14. Is this true or false? Think about what you'd have to show if it's true and what you'd have to show if it's false. So -7 divides 14. This is true. Why? Because 14 is equal to -7 times -2. So that's okay for these things to be negative. Remember, we just say these are just integers. A, B, and C are all integers. And that's, those are allowed to be negative. And so this is okay. So -7 does divide 14. Let's take a look at a weird one. I say it's a little bit weird, but it's actually helpful. This next example actually helpful to understand this terminology. Let's say 10 divides 0. So is this true? Does 10 divide 0? Can I write 0? Remember what that means for 10 to divide 0. That means I would have to find an integer c such that 0 is equal to 10 times that integer. Well, can you think of such a thing? Sure, why not 0? So 10 divides 0, this is true. This is a true statement since 0 is equal to 10 times 0. In fact, we can do a general result. Maybe you're already thinking this. If you're already thinking this, great job. Any number divides 0. Any integer divides 0. For all a in the integers, a divides 0 since I can always write 0 equals a times 0. Since 0 is an integer, it follows that a divides 0. So any integer is a divisor of 0. However, I want to turn your attention back to the definition of dividing, of divides. We throw out this case when a is equal to 0. We don't want to think about the 0 dividing anything else. And in fact, the way we've defined this, it doesn't make sense to say 0 divides anything else. So just remember that we can never say 0 divides anything. It just doesn't fit the definition. Let's take a look at another one, because both of these are cases when I wrote a true statement. So how about a false one? Something like 8 divides 20. All right, does 8 divide 20? Well, no. How could we show this? Think about it for a second. How can I show that there's no integer c such that 20 is equal to 8 times c? Well, notice, so this one was true, this one was true, this one's false. And that's, well, notice that 2 times 8 is 16, and 3 times 8 equals 24. Now, since 20 is between 16 and 24, and I only did a one integer gap here, we sort of skipped over 20, which means I won't be able to find an integer for which an integer c such that 8 times c equals 20. So there are no integers c such that 8 times c equals 20. Right? The integer would have to be between 2 and 3, and that's impossible. All right, so that's the idea of divisors. This takes a second to get used to. There's some sort of flipping around that can be a little bit confusing at first, but as you work through examples and try a few proofs, you'll start to get the hang of it. So just remember, practice is going to help you here for understanding this. All right, so let's take a look at one property of divisibility, and that is the following theorem. Let a, b, and c be integers, and of course with a not equal to 0. If a divides b and a divides c, then a divides their sum, b plus c. So just a quick note about proving things like this. So here we're proving an implication, right? So we'll get to assume that a divides b and a divides c. So what does that mean? Remember, that means that I can write b equals a times some other integer x, let's call it. And a divides c would mean I can write c equals a times some other integer y. Remember, this is like even and odds. It's important to remember to use a different variable for these. We can't assume it's the same one. And then think about what we have to show. So what do we have to show? We need to show that a divides b plus c. So our goal here in this proof is going to be to find let's call it z, find some integer z, such that b plus c is equal to a times z. That's our goal, is to find this integer. So if we want to show something divides something else, we need to produce this integer, right? It's an existence proof. There exists some number, some integer that satisfies this. And then if we know, right, that a divides b, that means we're given that integer, and then we can use it. So let's go ahead and try and prove this thing after what we just talked about. And in a lot of ways, this whole chapter is going to sort of generalize what we did with even and odd integers. We'll start with just divisibility, right? An even integer is just a number that's divisible by 2, or some number for which 2 divides that number. That's all even means. So this is really a generalization of that. All right, let's go ahead and prove this. So we'll start by assuming that a divides b and a divides c, and then we'll just write out what that means using what I just talked about there, right? We'll just use the definition of division, of divisor. So a divides b and a divides c, then say b equals a times x and c equals a times y, where x and y are integers. And now remember what I want to conclude here. I want to write b plus c as a times some other thing. And so how about I take this equation that we have and this equation that we have and add them together. That way I'll get b plus c on the left-hand side, and we'll see if that does anything for us. Then b plus c is equal to a times x plus a times y. Remember, we want to write a times some other integer. So this is, again, it should remind you of what we did with evens. If I want to show something's even, I need to factor a 2 out. Here, if I want to show that a divides something, I need to be able to factor an a out. So this, and we can do that here, right? ax plus ay is the same thing as a times x plus y. And so x plus y, we're sort of figuring this out as we go. Z is x plus y. That's that other integer. And it should be clear that x plus y is an integer because x and y are both integers. So I'll say, since x plus y is an integer, it follows that b plus c, or sorry, it follows that a divides b plus c, since we have b plus c written as some integer, x plus y, times a. And that's the proof. So it's not that bad. All right, let's take another look at let's take a look at another divisibility property on the next slide. So the previous result actually generalizes a bit more. We can say more, right? If a divides b and a divides c, we can say more than just a divides b plus c. In fact, a will divide any linear combination of b and c. So what that means is a, b, and c integers. If a divides b and a divides c, then a divides bx plus cy for every 2 integers x and y. So no matter what I stick in for x and y, a will divide bx plus cy. So since this is a universal statement involving x and y, I need to keep x and y general. And then I know a, b, and c are some fixed but arbitrary integers. Let me just think of a real quick example here. So an example of this might be, we know that like 3 divides 6, and 3 also divides 9. Then 3 is going to divide any linear combination of 6 and 9. So we know it'll divide 15. That was the last result, that 3 will divide their sum, so 3 will divide 16. This is saying a little bit more, that also 3 will divide, say, 6 times 2 plus 9 times 3. So that's 12 plus 27, 39. So that's equal to 39. I don't want to write that. That's equivalent to 3 divides 39. So since we know it divides 6 and 9, this theorem will tell us it also divides 39, and in fact it tells us it'll divide any linear combination of 6 and 9. So that's the idea here, and really we're just going to use a little bit more leverage here. It's going to be very similar to the last proof. So again, we'll assume A divides B and A divides C. Since I have X and Y floating around, I can't really use those again in this definition. So why don't I use, I don't know, D and E. So I'll say B equals A times D and C equals A times E for some D and E in the integers. Again, so now I want to make a statement about bx plus cy. I want to write bx plus cy as some integer times a. So instead of just adding these together, I'm going to multiply by x first in the first one, and then y in the second one. And then I'll add them together. Then bx is equal to a times d times x, right? And cy is, so c was here, so a times e times y. Hence, what happens when I add them together? Bx plus cy is what? A times d times x plus a times e times y. And the claim is that a divides this. Well, can I factor out an a or not? Well, certainly I can. Both terms have a factor of a times dx plus ey. And certainly since x and y are integers and d and e are integers, dx plus ey is an integer. So I'll say since dx plus ey is an integer, we can say for sure now a divides bx plus cy. Great. Another proof. So I want you to remember back to chapter 5 for a second, where we talked about relations. With this new terminology of A divides B, we could, if we wanted to, define a relation on the integers. We could say A is related to B if A divides B. Something like that might work. That would define a relation on the integers. What this next theorem is saying is that if we did that, the relation would be transitive. It would have the transitive property. That is, if A divides B and B divides C, then it follows that A divides C. So let's try and prove this one. So again, we'll start with our assumption. Assume A divides B and B divides C. Then we'll write these out using the definition of A divides B and B divides C. So then B is equal to A times X for some integer X, and C equals B times Y. So here X and Y are integers. And I'd like to make a statement. I'd like to write C as A times some other integer. So what I can do is, notice here I have B equals A times X. What if I take that and substitute it in for B? Right? If my goal is to write C equals A times some integer, and I have a C equals equation here, well, one thing to do would be to look for another equation that we can sub into that. That's sort of the logic behind why we might want to do that. Then we can write C equals, so here I'll substitute AX in for B, C equals A times X times Y. Remember that this bit here is really just B. And well, that's pretty much it. Maybe I'll just write it with some parentheses, even though we know it doesn't matter since multiplication is associative. So A times X times Y. And we know XY is an integer because X and Y are both integers. So since xy is an integer, it follows that a divides c, since we have c equals a times some integer. And so that's the transitive property of divisors. All right, now that we have talked about some properties and proved a couple properties, let's prove a result. This one might be a little bit surprising. The idea is for every integer n, for every non-negative integer n, the integer 4 divides 5 to the n minus 1. So again, what this is saying, so maybe I'll make a little table here, n and then 5 to the n minus 1. So here we're considering non-negative integers n, so that means we start at 0. 0 is the first non-negative integer. 5 to the 0 is 1, minus 1 is 0. And 4 does divide 0, right? So that would be true in this case. So let me write here 4 divides 5 to the n minus 1 as a statement. And this would be true. That's the value of that statement there. So if n is 1, 5 to the n minus 1 would be 4. And 4 divides 4, right? True. If n is 2, here we'd get 25 minus 1, we'd get 24. And 4 does divide 24, right? Because 24 is 4 times 6. So that's true. Maybe let's just do one more because it's going to get big really quick. 5 to the third is 125. 125 minus 1 is 124. Does 4 divide 124? Well, one thing you can do for 4 is divide by 2 and then divide by 2 again to find the divisor. So that's 62, that'd be 31. Yep, so 4 divides 124 because 4 times 31 is 124, so this would also be true. And so this result is claiming that for every positive integer n, this statement will be true. Now, this one we can't really do directly. It'll sort of be, you could try a direct proof on this and it'll sort of get out of hand pretty quickly. However, this responds nicely to induction because this is, right, it's a statement about all non-negative integers n. And so we're going to try an induction type proof on this. I'll write in parentheses by induction. And what would be our base here? Well, we're talking about non-negative integers, so our smallest one would be 0. We've already seen that that's true, but I'll write it out for posterity. By induction, so if n equals 0, then 5 to the 0 minus 1 is equal to 0, and 4 divides 0. So our base holds. What's going to be our induction hypothesis? Well, it's going to be that 4 divides 5 to the k minus 1. So assume 4 divides 5 to the k minus 1 for some integer k with k greater than or equal to 1. Since we already proved the k is 0, we can assume k is greater than or equal to 1. And we want to show that 4 divides 5 to the k plus 1 minus 1. So let me write this in red maybe. Want to show that 4 divides 5 to the k plus 1 minus 1. So that is, we want to find an integer such that 5 to the k plus 1 minus 1 is equal to 4 times that integer. So let's write out 5 to the k plus 1 minus 1 and see if we can't do some work here. So let's say, notice that 5 to the k plus 1 minus 1 is equal to 5 times 5 to the k minus 1. So what I'm going to do here is I'm going to split this up. So this is the same thing. I can write this as 5 to the, how do I want to write this? I have 5 to the k's. I just want to pick out 4 of them. So this is 5 to the k plus 4 5 to the k. I'm going to split that up, -1. Actually, I want to do the opposite of that. Because I'd like to, so what I'm doing here is I'd like to use my induction hypothesis that 4 divides 5 to the k minus 1. So I'd like to have 5 to the k minus 1 written somewhere over here. And so I'm splitting up my 5 to the k into 2 groups, 4 of them and then 1 of them. So actually, let me just rewrite this whole line. 4 to the 5k, or 4 times 5 to the k plus 5 to the k minus 1. So all I did was split up the 5 to the k. Now 5 to the k minus 1, we know by the induction hypothesis that that must be 4 times some other integer. So I'm going to write that up here. Assume 4 divides 5 to the k minus 1. We can write 5 to the k minus 1 equals 4 times x, for x in the integers. So we know that that's true. And so I'll use 4 times x for 5 to the k minus 1 here. So this is equal to 4 times 5 to the k plus 4 times x. And I'd like to say, remember our goal here, we want to say that 4 divides 5 to the k plus 1 minus 1. So I want to write this thing as 4 times something else. So here I can see I can factor a 4 out. So again, this is just like the evens, right? If we can factor a 2 out, it means it's even. If we can factor a 4 out, it means that 4 divides that number. So this is 4 times 5 to the k plus x. And clearly this will be an integer. 5 to any power is an integer, and x is an integer. So I'll say since 5 to the k plus x is an integer, 4 divides 5 to the k plus 1 minus 1. And so we've done the induction now. We assumed the induction hypothesis, and we proved the next value. So by induction, the result holds for all n. And that's our proof. All right, that's it for this video. In the next video, we'll start to talk about prime numbers, and we'll see divisibility come up there. All right, see you then.